Now we've already done a problem like this by using our augmented matrix, but it's also easy to take the inverse matrix and to use that to find the solution for x1, x2, and x3. So here I have a system. Now to write this as a matrix equation, I need to define three new matrices. And you'll notice that those three matrices look a lot like what we started out here. The matrix A is called the coefficient matrix. It contains the coefficients of the variables from the left-hand side here. So in the first row I see 1, 2, and 0. That's because I had 1x1 plus 2x2 plus 0x3 in the first row. And you see that the second row of this matrix A is 1, 1, 1. That's because I had 1x1 plus 1x2 plus 1x3 in the original system. And the same thing for the third row. The matrix X is our variable matrix, and it contains our variables, x1, x2, x3. And the matrix B is called the constant matrix, and it contains the constants from the right-hand side. Now what remains to be seen is how that these three matrices work together to give us the system that we see above. So let's take the matrix A times the matrix X. So I'm going to take that 3 by 3 times a 3 by 1, and when I take a 3 by 3 by a 3 by 1, that gives me a 3 by 1. So when I take the matrix 1, 2, 0 in the first row, 1, 1, 1 in the second, 1, 1, 2 in the third row, times the column matrix with x1, x2, x3, well, if I take the first row times the first column, I'll see that I get 1x1 plus 2x2 plus 0x3, which just gives me x1 plus 2x2. What's a little bit different here is these actually have variables, so we can't simplify any farther. When I take the second row times the first column, I get 1x1 plus 1x2 plus 1x3, which gives me x1 plus x2 plus x3. Third row times the first column gives me 1x1 plus 1x2 plus 2x3, which gives me x1 plus x2 plus 2x3. So when I multiply A times x, what I get is a 3 by 1 where the entries were simply the left-hand side of the system of equations that we saw on the previous slide. Remembering that B is just a column matrix with 22, 11, and 20, when I write AX equals B, I'm essentially saying that the two 3 by 1s that I've just talked about are equal. So if those two matrices are equal, that means that x1 plus 2x2 must equal 22, x1 plus x2 plus x3 must equal 11, and x1 plus x2 plus 2x3 must equal 20. That's just the system of equations that we talked about before. So the systems of equations from the previous slide is exactly the same as writing the matrix equation AX equals B. So these are equivalent to the original system of linear equations. The reason why this is especially useful is because if we were just dealing with real numbers and we had something like 2x equals 10, you could multiply each side by the multiplicative inverse of 2, or 2 to the negative 1, which is a half, and that would solve the equation. So if I take 2 to the negative 1 times 2x, 2 to the negative 1 times 10, well, that's the same as multiplying 1/2 times 2x and 1/2 times 10, and that just simplifies to x equals 5, and that's the solution to that real number equation. Well, what we're dealing with here is now a matrix equation, AX equals B. And we could multiply each side by the multiplicative inverse of A, which is A minus 1, and solve it for the variable matrix X. So if I take the multiplicative inverse A times AX and the multiplicative inverse A minus 1 times B, well, A inverse times A, remember that's just the identity matrix. And I times X, well, the identity times anything is just that anything. So that tells me that my variable matrix is just the inverse of A times B. And be very careful here. You have to do it in this order. If I multiply it on the left in the very first line, I need to multiply by the left when I look at the other side of the equation. Because when you switch around multiplication with matrices, you don't necessarily get the same thing. So what we have is AX equals B, with A being the 3 by 3 matrix that we talked about before, with 1, 2, and 0 in the first row, 1, 1, 1 in the second, 1, 1, 2 in the third, and the constant matrix being 22, 11, and 20 in one single column. Well, using our graphing calculator or by hand, we find that the inverse of A is the matrix with the first row being 1, 2, -2, -1, 0, 1, and in the third row 0, -1, 1. So in order for us to work out what the solution is for x, we need to take the inverse matrix that we just have shown above times b. So here's my inverse matrix with those 3 rows, and now I'm going to multiply that times the column matrix of the constants, which is 22, 11, and 20. First row times first column, so 1 times 22, 2 times 11, -2 times 20, and then I add them all up. Second row times first column, -1 times 22, 0 times 11, 1 times 20, and then I add them all up. Third row times first column means 0 times 22, -1 times 11, 1 times 20, and then I add them all up. So now let's simplify those 3 rows that I have there. And when I simplify them, I see that 22 plus 22 minus 40 gives me 4. -22 plus 0 plus 20 gives me -2. 0 minus 11 plus 20 gives me 9. So that means that the solution to this system, remember this is the x here that we're looking for, and the x, the variable matrix, consists of x1, x2, x3. So the solution to this system is x1 is 4, x2 is -2, and x3 is 9. What makes this method so powerful is if for some reason you kept the same A, you wouldn't change your inverse matrix. It would be exactly the same. But you could change the B here, and you could try many different choices for B. All that would do is change this column matrix, so you just have to do the matrix multiplication over again. If you were trying to solve this by an augmented matrix and you were to change your B, you'd have to redo that huge problem all over again. Here, all you have to do is change the column for the B and do the matrix multiplication. So in that sense, if you're doing a problem with many different sets of constants on the right-hand side, it's easier to do inverses. If you're just solving one system of equations, it's probably easier to use Gauss-Jordan elimination and work out what the solution is that way.